Hello everyone, welcome to my channel. This is Jayanti and I am going to teach you power system. Today we will discuss about how to calculate inductance due to the internal flux. We had seen about the inductance of a transmission line, and today we want to calculate and determine the inductance due to the flux inside the conductor. Let's start. See, inductance of a single conductor, it means there is a single conductor which carrying current and its returning path is at the infinity, and we will express or developed expression for flux linkage of an isolated path lying at infinity. Axis will form a single turn circuit, and magnetic flux lines are concentric closed circle with direction given by the right hand rule. Here in yesterday's class, in previous class, I discussed about how to find out the direction of the magnetic field in a current carrying conductor by right hand rule, or it is also known as thumb's rule. See, I am making this is our right hand, like this we fold like this, and a current carrying conductor, we hold a current carrying conductor like this, and current is flowing upward direction, and here the magnetic field is like our finger direction. It means if current carrying in a direction of thumb, it means our magnetic field in that particular conductor is in the direction of the folded finger, this direction, like this. Okay, now to calculate the inductance of a current, it is necessary to consider the flux inside the conductor as well as the external flux also. Means if there is a conductor, if it is a conductor and here current is passing through this, current is like this, and how is the magnetic field are this, like this, and in which direction? In this direction. If current is in the right hand side, then downward side is the magnetic field's direction. It means here the magnetic fields always in the inside conductor, it links the magnetic flux links outside the conductor, and it links also inside the conductor. Okay, so we have to find out the inductance due to the inside due to the flux that is inside the conductor, and we have to also find the inductance due to the flux outside the conductor. And today we only calculate the inductance in due to the internal फ्लक्स. इसका मतलब ये है कि हम लोग आज क्या करना चाहते हैं कि जो हम लोग का किसी कंडक्टर, जैसे ये मेरा कंडक्टर है, तो इसमें अगर फ्लक्स है तो फ्लक्स क्या है, मेरा इनसाइड भी है और आउटसाइड भी है, पूरा कंडक्टर में है, इनसाइड में भी है और आउटसाइड के कुछ पोर्शंस में भी होता है. तो इन जनरल हम लोग को क्या निकालना है, इस कंडक्टर का टोटल इंडक्टेंस क्या होगा, इंडक्टेंस इंटरनल इंडक्टेंस प्लस एक्सटर्नल इंडक्टेंस. एक्सटर्नल इंडक्टेंस किसके वजह से, जो मेरा मैग्नेटिक फ्लक्स है, इसके वजह से एक्सटर्नल इंडक्टेंस, और जो इंटरनली लिंक कर रहा है फ्लक्स, उसके वजह से क्या होगा मेरा इंटरनल इंडक्टेंस। तो हम लोग को क्या फाइंड आउट करना है, इंटरनल इंडक्टेंस। ठीक है, इसमें हम लोगों को एक और चीज़ जानना है कि इन ए कंडक्टर से we are seeing the cross sectional view of a conductor. See, this is the cross sectional view. See, it is like this cross sectional view of a conductor. In it, if we move surface to the center, if we are moving towards the center from the surface of conductor, it will seen in AC that there is some decrease in the current. It means the current flow in the surface of conductor is maximum as compared to the center of that conductor. Here मतलब देखिए, अगर हम लोग ये फेरेंटी इफेक्ट के वजह से होता है, और फेरेंटी इफेक्ट हम लोग फर्दर देखेंगे कि फेरेंटी इफेक्ट क्या होता है डिटेल में फर्दर पोर्शन में। इसमें हम लोग को क्या देखना है, देख रहे हैं कि अगर कोई मेरा एक कंडक्टर है, तो इन अ करंट कैरिंग कंडक्टर, इफ वी मूव फ्रॉम surface of that conductor to the center, there is decrease in the current. Okay, and also I want to say one thing, that there is flux always link, if external flux, if there is external flux, okay, external flux always links the total current inside the conductor. Okay, now moving to the next part. See, internal conductor. Here, internal inductance. Here I am making, here this is the figure for cross sectional of a long cylindrical conductor having a radius r, here it is, and carrying a current that having the RMS value is what, I. Now for calculation, here the MMF rounds a concentric closed circle path of radius x internal to the conductor as shown in the figure. Here we consider a distance that is x, and for loop integral, as we know that Ampere's circuit from Ampere's circuital law, here loop integral is equals to the current in that closed path. It means loop integral of hx dl is equals to ix. Here what is the hx? Hx is the magnetic field intensity at a distance of I. Here magnetic field intensity at a distance of x. And what is dl? Dl, we are taking a dl is a minimum distance of that particular conductor. What does distance means? Distance means see, if this is a conductor, okay, but at a distance of x, we are taking a part of that conductor apart. It means, see, this is the part is called dl, okay, length l at a distance of x. This is the equation number 13. See, here as I told you that hx is the magnetic field intensity having a SI unit ampere turn per meter at a distance of x meter from the center of the conductor. And what is the ix? Ix is the current enclosed up to distance x, since the field is symmetrical. what we are considering here, wait, we are considering that in that particular distance of x, there is a same magnetic field intensity in this circle. Okay, it means it is a symmetrical form. Field is what? Field is symmetrical. Symmetrical means in the distance of x there is same magnetic field intensity all over the कंडक्टर. मतलब देखिए, अगर मेरा कोई एक कंडक्टर है तो x डिस्टेंस में हम लोग का क्या होगा, सेंटर से x डिस्टेंस में मैग्नेटिक फील्ड इंटेंसिटी क्या होगा, ऑलवेज इक्वल होगा. ठीक है. नाउ हम लोग क्या करेंगे कि एच एक्स तो हम लोग का कांस्टेंट है, एच एक्स कांस्टेंट ले रहे हैं, तो डी एल पार्ट को ले रहे हैं. We are taking the integration of dl. It means the distance of that particular circle. Distance is what? 2 pi x circumference of that circle in a distance of x. Okay, so here we put the integration of dl is what? 2 pi x into hx equals to ix. It is equation number 14. Now we are assuming that current density in that conductor is always equal. Here we neglecting the Faraday effect that says that the current towards moving the center is always decreasing. मतलब कि अगर हम लोग कोई भी कंडक्टर में सेंटर की तरफ अगर जाएंगे तो क्या होगा, करंट मेरा रिड्यूस होगा. और इस यहाँ पे हम लोग क्या किए हैं, उस चीज़ को नेग्लेक्ट किए हैं. ये क्या है, मेरा Faraday effect है. Okay, here we are neglecting the Faraday effect, so that is why we are considering the current inside the conductor is uniform. That is why the density is also uniform. Density is also uniform. It means at a distance x, density is what? Ix upon my pi x square. It is the area. Density is what? Density is current per unit area is equals to density at a distance r, that is whole radius, I upon me pi r square. We are taking this. From here we can calculate ix. This is the ix and it is equation number 15. Now putting the value of ix in equation number 15, we get like this, and we get hx. Hx is what? Magnetic field intensity at a distance of x. This is the value of hx. See, for a non-magnetic conductor with constant permeability mu0, the magnetic flux density Bx at a distance of x from the center. Now we are going to find out the magnetic flux density. And what is the formula for magnetic flux density? That is Bx is equals to mu0 hx. What is mu0? Mu0 is the permeability in a free air. That is, it is permeability of a conductor in a free air. Okay, Bx is equals to this. Now here we putting the value of hx from equation number 16, we get this, equation number 17. Now the differential flux d phi x for small region. We are taking small flux for a small region, that is dx. Okay, here see, we are taking that dx for a small region. We are taking magnetic flux linkage. Okay, here we taking the magnetic flux, differential magnetic flux for small region, that is dx. And 1 meter length of a conductor, 1 meter length, what it says, see, this is the conductor. Okay, now we are taking in a 1 meter length, मतलब कंडक्टर का लेंथ कितना होगा, 1 मीटर होगा, और उसका थिकनेस ये वाला थिकनेस कितना होगा, ये वाला थिकनेस कितना होगा, dx, बस dx लेंथ कितना लिए, 1 मीटर लिए, और थिकनेस कितना लिए, dx थिकनेस लिए हम लोग. ठीक है, तो मैग्नेटिक फ्लक्स निकाले हम लोग, क्या डी फाई निकाले, डी फाई इक्वल्स टू मैग्नेटिक फ्लक्स डेंसिटी इंटू एरिया हो जाएगा आपका क्या, dx इंटू 1, एंड मैग्नेटिक फ्लक्स डेंसिटी क्या है मेरा, bx है. अब इस पोर्शन में हम लोग क्या करें कि फ्रॉम इक्वेशन नंबर 17 वी पुट द वैल्यू ऑफ bx in this equation and we get equation number 17, that is d phi x means flux linkage for a small region, that is dx is equals to mu 0 I upon 2 pi r square into x dx. Okay, it is for small region, that is dx. Now the flux d phi x links only the fraction of the conductor. See, we are taking the d phi x, it is linkage only for the dx region. It means it only links a fraction of that conductor. It means if conductor is like this and we are getting d phi x यानी flux linkage for that particular region, this region, for this region only. Okay, it means it is the fraction of दिस कंडक्टर. इसका मतलब कि हम लोग जो ले रहे हैं डी एक्स फॉर पर्टिकुलर स्मॉल रीजन के लिए, स्मॉल रीजन क्या लिए हैं, डी एक्स लिए हैं, और फ्लक्स लिंकेज जो डी एक्स में करेगा वो क्या होगा, एक फ्रैक्शन होगा. किसका फ्रैक्शन होगा, जो फ्लक्स लिंकेज मेरा कर रहा है टोटल कंडक्टर में. इट मीन्स the flux linkage for a region dx is a small fraction, it is the fraction of the flux linkage of that conductor. Okay, here what is the fraction, here it is pi x square upon में pi r square, this is the fraction. Okay, now flux linkage. Now the flux linkage, we known the flux, we find the flux. Now we move to the flux linkage. Flux linkage is what, d lambda x, this is the flux linkage for that that particular distance, that is dx for particular region, dx region, it is equals to this pi cancel here. It means it is actually pi x square upon में pi r square into d phi x. Flux linkage is what, flux linkage is flux in a particular area, यानी flux in a area is flux linkage. So here pi cancel and we get this equation by putting the value of d phi x from equation number. See here, what is the value of d phi x? See, it is the value of d phi x, and now putting this value in equation number, in this value here we put the value of d phi x and we got equation number 19. Now to get the total internal flux linkage we have to integrate both sides. So by integrating both sides from 0 to r, How 0 to R? 0 to R, this is the conductor, and from 0 to R we want to get the total internal flux linkage. That is why we are going from 0 to R. Okay, now for integration, this equals to lambda x, and for integration in this side we have to integrate x cube. Integration of x cube is equals to what? X to the power 4 upon में 4 limit 0 to R. Okay, now moving to the next slide. See here what we get. We are getting that x to the power 4 upon में 3 upon में 4 4, and from 0 to R, it means it becomes R to the power 4 upon में 4. R to the power 4 we have cancelled out. See, R to the power 4 here present, and R to the power 4 cancel out. Remaining is 1 upon में 4, and 1 upon में 4 into 2 is equals to 8 here. That is why it becomes mu 0 upon में 8 pi into I. We get this equation number 20, and by putting the value of mu 0 means permeability in free air is equals to 4 pi into 10 to the power minus 7. By putting this value we get this. This is the total internal flux linkage inside the conductor. This is the value of flux linkage inside the conductor. Now we want to find out the inductance of conductor due to the internal flux. And inductance is what? Flux linkage divided by current. And flux linkage here, flux linkage internal divided by I. By cancel out the I, we can get the internal inductance, that is the inductance due to the internal flux linkage in the conductor is become this. Here we seen that the total inductance due to the flux that links inside the conductor. यहाँ हम लोग देखें कि कितना इंडक्टेंस है, किसके वजह से, जितना कि फ्लक्स जो लिंक कर रहा है मेरे कंडक्टर के अंदर. जैसे ये मेरा कंडक्टर है, उसके इनसाइड में जितना भी फ्लक्स है उसके वजह से जो मेरा इंडक्टेंस आ रहा है वो कितना है. और यहाँ पे हम लोग देखें वी आर सीइंग दैट दिस inductance due to the internal flux is independent of the R. It means it is independent of the R distance from the center. It is independent of the R and it is always constant. ये हमेशा constant रहेगा. और हम लोग को जो total inductance है that is L equals to L internal plus L external. ये टोटल इंडक्टेंस फाइंड आउट करने में ये हमेशा क्या होगा, मेरा कांस्टेंट होगा. ठीक है. दिस इज़ इट फॉर टुडे, एंड इन माय नेक्स्ट वीडियो लेक्चर आई विल डिस्कस अबाउट द एक्सटर्नल इंडक्टेंस ऑफ अ सिंगल current carrying conductor. Okay, and this is it for today, and if you like my session, please like, share and subscribe my channel. Thank you, and please, as much as you can, please share this video. Thank you. Bye bye.